A 1.0 liter sample of an aqueous solution containing 0.10 moles of sodium chloride and 0.10 moles of calcium chloride. What is the minimum number of moles of silver nitrate that must be added to the solution in order to precipitate out all of the chlorine ions as silver chloride? Assume that silver chloride is insoluble. So we need to figure out how many moles of chloride are present within the solution overall. And so we have, for every 1 mole of sodium chloride, we will have 1 mole of chloride. So we will have 0.10 moles of chloride from the sodium chloride. And we will also have, for every 1 mole of calcium chloride, 2 moles of chloride ions. So we will have 0.20 moles of chloride from the calcium chloride. So that added together is going to give me 0.030 moles of chloride that needs to be captured. My ratio of silver to chloride is 1:1. So if I want to capture all of the chloride, I will need to go ahead and have at least as many moles of the silver as of chloride. And so answer choice C is going to be my best answer choice. In the reaction represented above, what is the total number of moles of reactants that are consumed when 1 mole of carbon dioxide is produced? So right here we have a ratio of 3 moles of carbon dioxide being produced from 1 mole of C3H8 and 5 moles of O2. And so if I just want 1 mole of carbon dioxide, I can just go ahead and divide all of these coefficients by 3, and then I will add these two values together. So 1/3 plus, not times, whoops, 1/3 plus 5/3 is going to give me 6/3, otherwise known as 2 moles. And that will be how many moles I would need in order of both of my reactants in order to produce at least 1 mole of carbon dioxide. According to the balanced equation above, how many moles of chlorite ion are needed to react completely with 20 mils of a 0.2 molar potassium permanganate solution? So we are going to go ahead and figure out how many moles of potassium permanganate we have present here. So X moles is equal to 20 mils. We will need to convert out of mils into liters, and then we will be able to use the concentration of 0.20 moles per 1 liter. So 20 times 0.2 divided by 1,000 gives me 0.004. And then I am looking for how much chlorite I would need to balance out this many moles of the potassium permanganate. Whoopsie daisies. And then I can go ahead and look at the balanced equation here. Now, for every 1 mole of potassium permanganate, there is going to be 1 mole of the permanganate ion. And my ratio of permanganate to chlorate is going to be, chlorite is going to be for every 4 moles of the permanganate, I will have 3 moles of the chlorite. My apologies, I keep saying the wrong compound. So 0.004 times 3 divided by 4 gives me 0.0030 moles, which is answer choice A. According to the balanced equation above, how many moles of hydroiodic acid would be necessary to produce 2.5 moles of iodine if I am starting with 4 moles of potassium permanganate and 3 moles of sulfuric acid? So I want to go ahead and produce 2.5 moles of iodine, and I can go ahead and figure out what my required relationship would be. I see that the relationship is double. I need twice the amount of hydroiodic acid as iodine, and so all I need to do is go ahead and take this and multiply it by 2, which would give me 5 moles. I don't care about these relationships here. Again, I am just asking about the relationship between hydroiodic acid and iodine, and their relationship is 5 to 10, otherwise known as 1 to 2. So I just need twice the amount of hydroiodic acid as iodine. The reaction of silver metal and dilute nitric acid proceeds according to the equation above. If 0.10 moles of powdered silver is added to 10 milliliters of a 6 molar nitric acid, the number of moles of nitrogen monoxide gas that can be formed is, so this is going to be a limiting reagent problem where I'm going to have to perform 2 calculations. So I can go ahead and figure out the moles of nitrogen monoxide that can be produced from 0.10 moles of silver. The relationship is 3 to 1, so for every 3 moles of silver, I can produce 1 mole of nitrogen monoxide. So 0.1 divided by 3 gives me 0.0333 continuing moles of nitrogen monoxide. And then I'm going to figure out if I have enough nitric acid in order to produce that amount of nitrogen monoxide. So I will need to figure out how much I could produce based off of 10 mils of my nitric acid. I'll need to convert out of milliliters. And then I will be able to go ahead and use the concentration. At which point I can go ahead and now use my relationship between my nitric acid and my nitrogen monoxide. So for every 4 moles of nitric acid, I have 1 mole of nitrogen monoxide. And so that will be 10 times 6 divided by 1,004. And I get 0.015 moles of nitrogen monoxide. Again, this is a limiting reagent problem. I do not have enough of the nitric acid in order to produce the amount of nitrogen monoxide that I could have produced based off of the amount of silver. So I am limited to the smaller of the 2 values, which is going to be answer choice A. When 100 milliliters of a 1 molar sodium phosphate solution is mixed with 100 milliliters of a 1.0 molar nitric acid solution, a yellow precipitate forms, and the silver ion becomes the concentration of the silver ion becomes negligibly small. Which of the following is correct in listing the ions remaining in the solution in order of increasing concentration? So our relationship here, whenever we dissociate, we're going to have 3 times as much sodium as phosphate, and our nitrate is going to be the same ratio as our phosphate. However, The silver is going to be bonding with that phosphate, so phosphate will be captured and will precipitate off with the silver. So the remaining phosphate is going to be the thing that we have the least amount of, because the rest of it was captured with the silver. Then we are just debating between if we have more nitrate or more sodium. Again, for every 1 mole of sodium phosphate, we have 3 moles of the sodium being dissociated off, versus for every 1 mole, we have 1 mole. So we are going to have substantially more sodium present than we would have nitrate present. In the reaction represented above, the number of permanganate ions that react must be equal to which of the following? 1/5 the number of iron ions that are consumed, 8 times the number of hydrogen ions that are consumed, 5 times the number of iron 3 ions that are produced, or 1/2 the number of water molecules that are produced. So what we're dealing with here, this is the balanced chemical equation. And so if all of the reactants are in exactly the correct proportion, then this first statement here, 1/5 the number of iron 2 that is consumed, would be correct. However, just because the balanced chemical equation has that relationship doesn't mean that that has to be true. We could have accidentally added much more of the permanganate ion than we did the iron ion, and that doesn't mean that our reaction isn't going to proceed or can't proceed properly. We can have an incorrect balance of our actual reaction versus the balanced chemical equation. Same thing for the reason why B is going to be incorrect as well. Again, we could have had more of the hydrogen ions being added for whatever reason, or not enough of the iron ions to completely match up with this balanced chemical equation again. 5 times the number of the iron ions that are going to be produced. This is not going to be true as well. Again, if we don't have the correct amount of iron, then we're not going to be able to go ahead and react this through. However, answer choice D, because oxygen is being limited and is a part of that permanganate, the half of the number of water molecules that are produced is going to be correct. We need the oxygen to come from that permanganate. This permanganate will directly impact the number of water molecules that are produced, and so that is going to be my best limiting factor. I have 1 oxygen for every 4 moles of water, and I have 4 oxygens here. So that means I could produce a grand total of 4 moles of water there, just from my pure amount of oxygen. And since it is contained within that permanganate, that relationship is set. What is the percent yield of oxygen if 12.3 grams of potassium chlorate with a molar mass of 123 grams is decomposed to produce 3.2 grams of oxygen with a molar mass of 32 grams, according to the equation above? So what I'm going to need to do is to go ahead and figure out how much of the oxygen I could have produced based off of this mass of the potassium chlorate. And then they already gave us the molar mass, so that's very nice. My relationship between my potassium chlorate and my oxygen is for every 2 moles of potassium chlorate, there are 3 moles of oxygen. And then it gives us the molar mass of oxygen is 32. Then I can go ahead and calculate that. So 12.3 times 3 times 32 divided by 123 and 2 gives me 4.8 as my predicted yield. I didn't get this yield. Instead, I got 3.2 grams. So my actual yield divided by my theoretical yield times 100 will give me my percent. So 3.2 divided by 4.8, this number times 100 gives me 66.6 repeating percent. Rounded up, that is going to give me 67% as my yield. Gases W and X are reacted in a closed rigid vessel to form gases Y and Z according to the equation above. The initial pressure of W was 1.20 atmospheres and that of X was 1.6 atmospheres. No Y or Z is initially present. The experiment is carried out at constant temperature. What is the partial pressure of Z when the partial pressure of W has decreased to 1 atmosphere? So my total pressure is going to remain the same for the entire system since I am not increasing the number of moles on either side. I have my relationship is 1 to 1. I'm not creating any new moles or anything like that. So if I replace one, I'm replicating it with another. So if I decrease my partial pressure of W to 1, that means 0.2 atmospheres must have been produced of my Z value. So that is answer choice A. 0.03 mole sample of ammonium nitrate is placed in a 1 liter evacuated flask, which is then sealed and heated. Ammonium nitrate decomposes completely according to the balanced equation above. The total pressure of the flask measured at 400 Kelvin is closest to which of the following? The value of the gas constant R is 0.082 liter atmospheres per Kelvin mole. Okay, so since we are going ahead and completely eliminating this, and we are creating 3 moles from that 1 mole, our sample needs to now be 3 times as many moles. And then we can go ahead and use the ideal gas law to figure out what the pressure is at that point. So ideal gas law is PV equals nRT. I now have 0 moles of my reactant, 1 mole of the dinitrogen monoxide, and 2 moles of water. And so finding P, we are going to have 0.09 moles total times our R value, which was given as 0.082 liter atmospheres per Kelvin mole, and then times our temperature at 400 Kelvin, and divided by our volume, which was 1 liter. Canceling out all of the shared units, I am left with just atmospheres, which is an appropriate unit for pressure, so that looks good. Then I could go ahead and type this in, so 0.09 times 0.082 times 400 divided by 1, same thing, is going to give me 2.952 atmospheres. And then I only get 1 sig fig, so this is 3 atmospheres, which is going to be answer choice A. What volume of oxygen is required to react with an excess of CS2 to produce 4 liters of the carbon dioxide? We're assuming that all gases are measured at 0 degrees Celsius and 1 atmosphere. We're also going to go ahead and assume that the actual size of the molecule is not going to affect anything. If I want 4 liters of carbon dioxide, I need 3 times as much oxygen. So 3 times 4 will give me 12 liters of oxygen being required to produce 4 liters of carbon dioxide, which is answer choice A.